How's the preparations going on? Good. Yeah, that's okay. It will take some time, but yeah, try to cover all the things so that you not miss like 4 months, and yeah, don't miss January or something.
Good evening, sir.
Good evening. All of you got your hall tickets? Who is writing exam? Exam is on 29. How much time you are having exam? Okay.
நம்ம எங்க இருக்கிறேன்?
Okay. We just start solving this session, and let us see whether you people having some doubts, or yeah, we got some messages that okay, we want to just go and check what are the possible question can come, something like that. Okay, we can anyway we can check this one, and if you people want one more session or something such that we can just try to revise all the things which we can conduct also. Okay, let us see. So this is our last week assignment. Yeah, this is your last assignment of this course also. So let's see. The first question is okay. You people are not seeing my window. Okay, sure. Can you people see the window? Can you
Yes,
people?
sir.
Yeah. Okay. Now, there are some direct questions and there are some numerical. Okay, this is yeah. The week 12 is pretty small sessions. Actually, it is like just a revisiting of some diffraction optics and some diffraction techniques. Okay, then we can go for the first question. Diffraction can be considered to be one is the reflected light, second one is refracted light, any light that is not reflected or refracted light. Next is a reflected or refracted light. What's actually diffraction? What is the diffraction? How the effect is coming? It's a universal effect or it's like a it's only come at some time. Whether the diffraction is always there or diffraction requires some particular condition to be noticed or something like that. Can you just give some insights about diffraction? We can open PowerPoint and see.
I think when the object is at the very similar to the size of the wavelength,
Yeah. That time, what happens?
so the wave theory is being applied there.
Uh,
So anything which is not reflection or refraction,
why diffraction is happening?
interference of the light.
Yeah, interference is the main thing actually happening. Interference between the wavefronts, which is actually emitting at different points. This is the main cause of diffraction. But what actually we call it as diffraction, it's like a bending of the light at the edges of some opaque object. And yeah, as the class progressed, we already seen that if you have an aperture or a opening, usually we say that light will travel in straight line. Okay, the normal case, light should travel straight line. If there is a opaque object which is stopping the light, on that portion light will get stopped and all other portion light will be traveling. This is the way you are seeing also, correct? Like this way. And if you put a screen here, you will get some intensity distribution on the screen. Okay, this is a normal case if you have a big aperture and if you put some light from one side and you measure that intensity at the other side, you will get something. And if you see exactly if the light is exactly traveling in a straight line, you will see that the distance this distance will be same. It will be something like a parallel thing. And actually these regions are called It's a geometrical shadow region. Okay, so there is no light falling at that point, and you will see light only at the exact size of your aperture. But if you do, you know that light is traveling in a straight line, and if you are expecting this one, but if you really do an experiment something like that way, you can see that if you use some big aperture, what will be like an aperture will be like nothing. This will be some big region, and just see that this, I'm saying this is circular aperture. I'm saying that all other portion is opaque, only this portion will be transmit the light. So if you put a beam of light here, if you put some beam of light here, what you can expect at the other side actually you can expect a geometrical shadow, and only at the portion where your aperture is present, that time you can see a large intensity. But if you really do an experiment, you can see that this edge is not going to be sharp. You can see that the edge is a little bit blurred, a little bit diminished, or it's like a, even though your aperture edge is sharp, the edge on the image is going to be a like a blurred. Why it's happening? This is happening because of the diffraction. Even though you are not seeing the effect of your diffraction in a completely proper manner, you can see actually this diffraction effect is a universal thing. You cannot avoid diffraction. A diffraction effect will be always there. But the thing is that how diffraction effect is actually coming in your imaging or in your measurement of the data. So there are conditions in which diffraction will dominate over all other things. That condition is actually given like your aperture dimension is almost like your dimension of your wavelength. So that time the diffraction effect will be much more. In that case, what you have to do, anyway, you cannot change the wavelength of the light. So what you do, you just make the aperture size much smaller. Aperture size much smaller compared to the wavelength of the light. Then on the screen, what you are going to see, just say that this is your aperture size is almost like a some 500 nanometer. I saw that this is something like a big size. I'm saying that this is like a 5 centimeter. You can see that this size is almost like 5 centimeter, and there will be some blurred region will be there at the geometrical shadow region here. Now see that this is like a pinhole having a dimension of 500 nanometer. What are you are going to see here? Just tell. This is the aperture, this is the screen. What you are going to see on the screen? Just tell. You are using some red light or some green light. What you are going to see here? An idea? And tell. This is a aperture of 5 centimeter, and you are seeing it on a screen, and now it's an aperture of 500 nanometer. What you are going to see here? Tell.
Concentric circle.
Yeah, what you are going to see, you will see a some central maximum, and it will not be exactly like a 5 centimeter, it will be some more bigger. Then you will see some minimum region around, again some maximum circles, again you see some diminished circle, like that way what you are going to see. So if you think that light is actually traveling in a straight line, whatever the light came here, it should reach here. But there is no light which is actually coming from this side, because here there is no light is coming from here to reach here. To reach here, there is no light is coming from here. So what's happening? Because whenever you are sending a beam of light here, the light is going to bend, and it is traveling at the geometrical shadow region. It's not like light is just bending and passing on the geometrical shadow region. There are some conditions are getting satisfied. Light is bending, and the bended light, the light which bend is undergoing interference, and wherever they are getting constructive interference, there you are getting maxima, where you are getting destructive interference, where you are getting minima. As a result of this combined bending as well as the interference of the light, you are getting a concentric circle, and this effect is called diffraction. And the diffraction effect is actually completely different from your reflection as well as a refraction. So you can say, if you are seeing an imaging and you are seeing that either you can happen, if there is a medium, it can happen undergo reflection, or it can pass through solely refraction. Okay, if there is an opaque object, that will be like a transmission. Yeah, transmission, you can say it's like either refraction or it's like a normal transmission without any medium. That can happen. But if you are seeing anything phenomena other than this reflection and refraction, or it's like, it will be, what will be that one? It will be like a bending, and you are seeing, if the reflection also, it is actually following certain rules and laws of reflection. The refraction also, it is following certain rules, that's Snell's law. But you can see there's a completely different phenomena which is actually different from reflection and refraction. Light is bending at the edges of some opaque object and is falling at the geometrical shadow region. Other than just falling at the geometrical shadow region, also you can see that there are some interference effect is happening between. So you cannot actually explain this in with the particle particle nature of the light. You have to require wave nature of the light to explain. So this is like, you can say that the phenomena which is not included as reflection and refraction, and that's actually a universal phenomena. You cannot avoid diffraction also. The thing here also, diffraction is happening, but that your normal light transmission effect is actually dominated over diffraction, such that you can see only diffraction effect very less as the blurring of your edge. But in this case, actually, other than the blurring of the edge, whatever you are going to see, you are see the concentric circle and the geometrical shadow region where the light not supposed to come. So this here actually diffraction effect is dominating. Why diffraction effect is dominating? So this condition is satisfied. The aperture size is almost equal to that of lambda. Okay.
Yes, sir.
Yeah. Now second question. Similarly, optical systems are typically only reflective, only refractive, only diffractive, both refractive and diffractive with one phenomenon is dominating. So you cannot say that this is the correct answer, but yeah, what is the most appropriate answer here? Optical system can be both refractive and diffractive. Yeah, along with it, you actually add reflective also, but yeah, all other questions are wrong. So you can say that this the fourth one answer is actually correct, or that is the most appropriate. The optical system can be refractive as well as diffractive, but depends on the structure or the size or the alignment or how we manufactured. One of the phenomena may be dominating. Either the diffraction effect can be dominated or the refraction effect can be dominated. This only happens in terms of the optical system through which light is passing. It's like if you want to compare refractive and diffractive in terms of transmission, or this diffractive can be in the reflection mode also. So it depends on the size of the or the nature of the aperture or the system. It is actually controlling which will be dominating, which effect will be dominating. If the size is somewhat comparable to that of the wavelength of the light, diffractive effect gets dominated. If the size is something like very big, then it's like a normal refractive effect or the transmission effect will be getting dominated. Okay.
Yes, sir.
Now see third question. This question also like comparatively simple. Which of the following statement is true regarding the frontal lens of shown in the picture? What they are doing? What is the frontal lens? In frontal lens, what is actually what you are doing? Did you see any frontal lens? You people see any frontal lens? I am sure almost you people may have seen. Did you see a normal lens?
Yes.
Okay, how it will look like? If you touch that lens, you can feel that some portion may be thick, some portion may be thin, depends on the nature of the lens. Okay, if you are seeing your eyeglass lens also, yeah, if it is a positive lens, you can see the middle portion is thicker compared to the edge portion. Okay, now this is just a refreshment. Okay, but I want to know that whether you people may have seen that frontal lens or not. Hmm. Anybody seen, or you can just remind whether did you see the lens or not? You may have seen. I am almost sure.
So I think maybe lighthouses.
Light,
Lighthouses.
lighthouses. Yeah. Okay.
Or that mini microscope, I
Mini
think. So they use an
mini
what is this?
microscope.
Like that lenses in a strip format or something.
Mini microscope. Hmm.
I'm not sure.
Okay. But one common thing, maybe yeah, you people may have seen that our some Chinese toy kind of thing, which is actually they say that okay, this is a projector for your mobile phone. You will put your mobile phone in some cover and you will see a big display kind of thing, some lens kind of thing. Did you see that one? It's like some low cost toy. It was something like a very popular, like I think almost like 3 or 4 years before. You can put a mobile phone, it will like a mobile phone stand, and there will be some lens kind of thing in front of, and it will show some bigger image of your mobile display. So you can see like a higher image of your mobile display. It's a magnified image. And you can see
Sir,
that, yeah,
sir, can you increase the volume of the audio, sir?
let's see. Now it's okay.
Little bit, sir. Little bit more, sir.
I check whether I have some control over my microphone. Not loading. Hello, whether this is audible? Am I audible
Yes,
now?
sir. Audible. Yes, sir.
I,
Audible.
yeah. Now how my voice is? Good or bad?
Ah, yeah, better, sir. Better.
Okay. I think it was in my camera's microphone that it did it.
Better, sir. Now.
Okay. Yeah. Now you people, whether you people see that device, that's like a simple device. So like, but you will see that If you touch that one, you will feel that it is not like a original lens. It will be like a plastic sheet. But what you will see on that plastic sheet, you will see a lot of circular rings. That's actually a frontal lens. You will see a plastic sheet, and it is, you will see like a concentric circle kind of thing above that. It will be a transparent plastic sheet containing a lot of concentric circle, but it will act as a lens. And similar thing you can see in, yeah, in your, if you are going and seeing mm, your lighthouse cameras, not sorry, lighthouse lenses. Lighthouse having a big bulb, and in front of there's a dome, and in front of there will be some focusing arrangement. And usually, yeah, that focusing arrangement will have a this kind of circle of things you can see. And these things are actually frontal lens. What they will do, actually, a normal lens, they will remove the 2 pi face part, and if there are some different face parts are there, they'll just cut out that portion, and they'll combine to form, because 2 pi phase difference is not going to give any change. So actually you don't want that effect. So they'll cut that portion and make this. This will be a complex frontal lens, but actually you can do a binary kind of thing also. So it will be something like this. This efficiency will be a little bit less, but yeah, this will be more. But constructing this kind of frontal lens will be very easy compared to this. You don't need to worry about your curvature and other things. It will be like very easy. Okay. So yeah, let's go to our question. You see, it is always refractive. This is a frontal lens. So always refractive. What is the question? What is the which of the sentence is true? Whether it's always refractive, whether it's always diffractive. If D and T are in the order of the wavelength of the light, it is more a refractive lens than a diffractive lens. If D and T are of the order of the wavelength of the lens, then it's a more diffractive lens than a refractive lens. What's the correct answer? Correct answer is there, but just tell that, yeah, why it is like that way. It's actually a part of a normal lens, and you remove the 2 pi areas. So just think that if you are, how the lens is working, how the lens is getting, making the light focused due to which phenomenon, the lenses using which phenomenon for focusing or making image, which is the common phenomenon.
Refraction.
Yeah, lens is using refraction. And how the refraction is coming, because of the difference in what?
Thicknesses.
Yeah, thickness is a main term, but yeah, as per the light, thickness means it have a term, normal thickness for anybody, but for the light, what the light is seeing, or what light experiencing, a thick,
Path length.
yeah, what the lens is or the light is seeing is a optical path length. So what happens in the case of a lens is seeing different optical path lengths at different position, and because of the changing the optical path length, the light is getting bent by Fermat's principle, and it is getting focused at the point. Similar thing we are doing in the case of a frontal lens also. So here actually what we are doing, we already know that path length is actually repetitive, uh, or path length corresponding to path length, there is a phase difference, and the phase difference is actually equal when you are adding a factor of 2 pi. 2 pi means or you are adding a path length corresponding to lambda. So if you are removing 2 pi effect also, there is not much difference between the light traveling from one place to another. Okay, you got it? see. Just think that a light wave is traveling at a particular distance. Now this is a one wavelength, this is another wavelength. Now think that light is traveling and it is reaching at a particular point. Now think that if I moved towards one more wavelength, so it will be like something here. Okay, this portion is actually after this one. Corresponding to this, surface, whether any difference happened with this particular wave or this particular wave. No,
It is the same.
yeah, for that particular surface, it's exactly that seeing the same kind of light at both the time, but actually there is a shift of this much distance. What is that shift? That's corresponding wavelength of the light. Or if you corresponding to, there is a path length or phase difference, that will be a phase difference of 2 pi. Okay, so in the case of a normal lens also, what is happening? There will be different path lengths light is traveling. And if you are saying that, okay, this is actually corresponding to exact path length, this portion actually you don't want. Okay, because after this one, this portion, whatever the light is traveling, is actually same. So actually you can make a lens something like this way. Because I only used the path length which came out of this. So only this portion I used, this portion I used, and this whole portion I used. Now I again measure. Then sometimes you may feel that, okay, this portion is actually coming as exactly 2 pi path length. So the light traveled from here to here is actually same as if it is traveled from here to here also. So you don't want this portion. So again you can change this old portion and corresponding to this new portion and the corresponding to other portion corresponding to this portion, corresponding to this portion. Okay, now you see, now you can see that if this distance t and this distance, now it will be in the order of how much, because now we are taking, because there is no more one full path length is here. So let's say that the distance was like something like a 3.5 lambda. Okay, and you removed 3 lambda here, then whatever is remaining is 0.5 lambda. So you are going to decrease the as much path length you don't want here, because the same path length is giving same effect, or the multiple of wavelength is giving the same effect. So whatever is going to remain here will be your path length in the order of your wavelength. So which is the phenomenon which is going to dominate there, because your the traveling size, the light is going to see some aperture which is having a dimension of the order of the light's wavelength itself. So which phenomenon is going to dominate there? Which effect will be dominate there? Then you will see that diffraction effect is going to dominate at that point than refraction. So actually you started with the refraction and you removed all your equal path distance as some offset and removed. But yeah, when it is reaching to the order of the wavelength, you can see that the effect of diffraction effect will be coming and is dominating more than your refraction effect. Okay, so it will be the answer. If D and T are the order of the wavelength, then it is a more diffractive lens than a refractive lens. Okay, so actually it will increase its efficiency. So anyway, that refractive effect is there. Along with because of the diffraction also, the bending of the light is happening. Because other than the effect of the diffraction, because now you can see that it is one portion. It's actually there will be some refraction is there. Other than this portion, you can see that there are a lot of edges are coming, and this each edges the diffractive effect will be more dominating than the refraction effect. Okay. Consider a reflective amplitude diffraction grating having a grating period of 2 micrometer. If a laser beam of wavelength 633 nanometer is incident on the grating with an incident angle of 30 degree, the angle of the first order reflection is, okay. First order reflection means it is not a simple reflection, it is actually reflection, it's a reflection grating. So what will happen? The diffraction effect will be coming in the same side of your incident wave. That is actually your reflection grating. Don't think that this is just a reflect like normal mirror. Okay. In the case of a normal mirror, what will happen? Just think that it's a normal mirror. What will happen? If an incident light is coming, at a particular angle of incidence, I call it just I, and
Reflection.
it reflect back,
It will be R. It is
it
the
will be
same.
R. And what's the relation between I and R?
Be the same.
I will be equal to R. Now you think that of a reflection grating. How it will be a reflection grating? This will be a reflecting surface, but you will have a different grooves. Okay. Either you can make it is in the form of a phase difference grating or an amplitude difference grating. I am saying that okay, I am making it something amplitude manner such that in between there will be no reflection. Okay, and this dimension is actually comparable with that of the wavelength of the light. What will happen?
Diffraction.
Yeah, if an incident wave is coming at an angle of incidence of I, there will be multiple, because this is actually in the order of a wavelength of the light. So what will happen? Other than like a normal reflection, actually there will be reflection at this direction. Sometimes some light may go in this direction. Why? Because your this actually bending of the light is happening. Now you see, so you cannot actually say that I is equal to R. There will be some component which will have exactly I is equal to R. But there will be some portions in which there will be some angle other than I is equal to R. Just say that this is actually R1. This is exactly I is equal to R, I am saying. But you can see that there will be some angle which I is not equal to R. What will happen if you are considering that there are like other waves also coming here, that will also reflect something like that way, and there will also something like this kind of thing, and there will be some path difference between this wave and the wave which is coming from here, the incident wave as well as reflected wave, but that wave which is reflected, which is not following the exactly same reflection. Okay, so I is equal to R will be like exactly following the same manner, and you will get a normal reflection spot here, but other than the normal reflection you will see some reflection which is actually coming because of the diffraction effect, and this light is getting constructively interfered. What will happen? You are going to get a bright spot, and if they are undergone a destructive interference, you are going to get a dark spot. So for a refraction grating of the grating parameter, like grating period of D, and the incident angle of I, and the refractive angle or the reflecting angle, this is I am saying that R. What is actually the condition for diffraction grating? D into
Sin I
sin I minus
and sin
sin
R
R will be equal to,
lambda.
yeah, it will
M
be
lambda.
m lambda. It will be some odd or some numerical or a whole number multiple of lambda. What you are going to get a constructive interference pattern. Okay. So now you come to your question. Having a grating period of 2 micrometer and the laser beam of wavelength is 633 nanometer is incident on a grating with an incident angle of 30 degree. The angle of first order reflection is. So you already know that they said that angle of first order reflection. So m is equal to 1, lambda is equal to 633 nanometer, d is equal to 2 micrometer, and you are given I is equal to 30 degree. What you want to know, or you don't know, or you have to find out. So
Sir, it is a minus or plus?
it's minus na.
But in some books it was being mentioned as a plus. Sin theta, sin I plus sin reflection. Plus it was being mentioned in some other book.
In our lecture it is like sin I minus sin R na. Just check. If you have a doubt, you can check, and then we can just go through also. No problem. Sorry.
Some other duty cycle say to use that direction. If I wanted that, is equal to n.
Oh, it is minus.
Minus na. Let us see.
Oh,
We have
yes.
some doubt. Let us see whether it will go for minus or plus. So this is your path length. So and one sin I. Yeah, it should be minus. Why it should be minus?
The difference in
Now you see that actually
AB.
this the total path length is coming from here.
Yes.
If you have only one type of ray, it's like that way. This ray, just like this portion is the A bar, B bar.
B bar.
This A bar,
B bar.
yeah, this A bar, B bar is actually giving the path length of the second ray. if you getting path difference from the second ray, again you are supposed to add that one. Now whatever you are getting here, actually a bar b bar is the path length of the second ray. That second portion is actually coming from your first ray, the reflected first ray. So the net path difference will be minus. So just think that if you have some reflection here and the reflection is actually contributed from your first ray, you are supposed to add. Okay, I don't know in that books, maybe how you are taking that one, you are supposed to see. Okay.
Okay.
Yeah. So if it is in the order of lambda, you are going to get a constructive interference. So now we know that d is equal to 2 micrometer. So I am converting it to nanometer. So d2 into 1000. Okay. Sine 30 degree minus sine r is equal to 1 into 633. Okay. So sine 30 minus sine r will be equal to 633 divided by 2000. What will be sine 30?
Half.
Sine 30 will be half minus 633 by 2000 will be equal to sine r. What is the value? 0.5 minus 633 by 2000.
It is 0.315, 3165.
Okay. Yeah, 0.3165 and 0.5 minus 0.3165 will be
0.1835.
yeah. So we are going to get a 0.1835 is equal to sine r, or r will be equal to
10.57.
sine inverse
10.57, sir.
okay. Yeah, r is to 10.57 degree. Okay, got it? So the answer is 10.57. So they are giving us some big range like 10.17 to 10.97 you can give. Okay. Now see, a phase grating having the ridge height of 700 nanometer and a grating period of 2.2 micrometer was used with a helium neon laser. This is clear now? The question about how to calculate this value. Fourth one.
Fourth one is correct, sir, but
Yeah.
I did it wrong. It is only the plus sign I used. For the angle, it came negative.
Okay, negative. How much you got?
The same. Negative, it is the magnitude is the same.
Okay. So you put as a negative.
Yeah.
Answer you put in. Okay, since it's a numerical, you can put negative also there.
Yeah.
Okay. Yeah. But you can think what will happen in the case of negative. Now you think that, so that can also be correct. Yeah. But the thing, yeah, there may be some sign change you may have to introduce there. But by logic, you just think if it's a reflection grating, it will be something like something kind like this. Okay, if it is seeing a normal reflection gate, it is something like this way, and you will see the light. They already said that the incident angle is 30 degree. So Normally in the case of a reflection grating, what you will see, there will be like a normal reflection. You can see that some light is traveling here, okay, and this will be your zeroth order,
Yes.
okay.
Yes.
And it can go here, here, like this way. So if you want to go to negative, how you will define it as a negative? Or you may be thinking that this will go like this much. So this is 0, you are thinking that this will be negative. So it will go like here, here, like that it will go. So your first order reflection you are getting from this side.
Right. It will be from the left hand side.
Yeah. So usually it will happen like this way. So you can actually calculate how it is coming. So if you're getting something like a sign problem, you can just check that whether you can just apply your logic and how they are getting measured here. And if you don't want, yeah, you can actually see, I don't, since I didn't see that actually how they are derived in that your that book, maybe they may have taken some negative effect when your reflection is coming, or something they may have taken, such that I cannot say that that is wrong. So there may be some convention they may have taken in such a way that whenever they are getting reflection from here, maybe something negative may be taking place, because when it is like transmitting, we are saying that maybe they are taking that whatever is coming in this direction means this y direction may be positive, or whatever is coming in the, oh sorry, the other way. If it is directly going from here to other side, they may be taking it as positive, and if it is coming back to the other direction, maybe taking it as negative or something they may have used the, such that in that case also I think you can get a correct answer. But I have only doubt that the convention which they are using, may you may have to follow to take that. That only I think you may have got some mistake. There will not be
Conversion.
yeah. So that only you have to check it
Okay.
when you are following a particular convention, because they may arrived at a particular equation using their own convention. Because you can see that some books like lenses equation, like they may see that 1 by u minus 1 by v is equal to 1 by f, they may have
Yeah,
reached.
that is right.
Yeah.
Sometimes you have plus also.
Yeah. So what they are using in that case, actually there are their own convention, like that way how it is moving from one place to another.
Right.
So that may not be the convention which we are using.
Okay.
So
Understood.
yeah, the equation is actually arrived from the convention. When you are taking that particular equation, you are supposed to stick on the particular convention, then it will not go wrong. Like equation may be look different, your convention also look different, but it will come together and give you a proper answer. Okay.
Right.
Now you see, a phase grating have a ridge height of 700 nanometer and a grating period of 2.2 micrometer was used with a helium neon laser of 632.8 nanometer wavelength with a normal incidence. The zeroth order had no light intensity with this laser source. If the laser source is changed to 488 nanometer, then the phase difference between the light passes through the ridge and valley of the grating is something rad. Okay, you got the question? What is the question says? You have a phase grating. What is actually phase grating? That is amplitude grating and a phase grating. Did you people see gratings actually? Anybody see gratings? Somebody I have done in a physics course or something may have seen grating. Raju sir, did you see grating?
No, sir. I am totally. I am from a different field.
No. You have an idea of grating?
Rating, yes.
You know how
It looks like
you know how it look like?
a glass lid.
Yeah, it will be actually, it will look like a some slide kind of thing, it will be there. But what is the difference? What you will see here on the on the on the slide, what you will see?
Minute lines, like fine to fine lines.
Yeah, the lines anyway you cannot differentiate it, but you will see something there.
So whether it can be used for a diffuse light or it is usefully in the illumination,
Illumination, actually, yeah,
where you want to concentrate the light just below the whole this one.
actually in the illumination portion also you can see some grating, but actually the grating will contain minute lines, but the lines will not visible because the lines will be in the order of the wavelength. That will be like some 500 nanometer, 600 nanometer width. So you cannot actually see the exactly the lines, but you will see something noticeable there. What is that one? If you see a grating, you can see that. Now when I am saying this one, you will see that you know some grating kind of thing. What you will see here, just tell. In a normal grating, what will be very easy to visualize? What you will see other than a glass slide? What is the difference which you will see on a grating? Physics people who see the gratings can just tell for the photonics people. What is the peculiarity difference between a grating and a glass piece? What you will see? Anybody see grating? I think most of them see grating also. You will see some rainbow color. You people remember?
Yeah, only at a particular.
Yeah. If you just uh, see grating at some particular angle, you can see some rainbow kind of color here.
Yes, sir. But not directly we can see that.
Yeah, that we cannot see, but other than a glass plate, what will be peculiarity of that thing? And this kind of rainbow color you may have seen somewhere also. Where you see? It is not in a square shaped thing, some circular kind of thing. You see some rainbow color. What is that? Some circular kind of thing. You see some rainbow color.
It is
CD,
that you
your
have seen
drawing?
in CDs and all.
Yeah.
Right.
Why you are seeing this rainbow color in your CD?
Yeah.
Because
Yes,
of
sir.
small the rings.
Yeah. Actually, one CD is actually a grating because
Yes.
the data is stored in like a that thing is it's like a pitch, and actually it is containing a lot of lines, minute lines, which is in the order of the wavelength. So if you cut a portion of your CD, it will, you can see it is actually a grating. But on a grating, actually you can see this is like a straight lines. But in the case of a piece of CD, it will be something like a curved lines. Only this is the difference. A CD is actually a grating. And I just to see this is like a, actually there are experiments like you can, so on the grating you see this grating equation now, some d sin I minus sin r is equal to m lambda. So yeah, if you, now you people may not have time, but if anybody have a laser torch, you know the laser light which we get from some festival or some fancy shop kind of thing, just take a CD, first take a normal mirror and put a laser torch here, laser light here. But you will see the laser is actually reflecting, and in some corner of your room you will see the laser spot. Now same thing you do with your CD. Take a CD, just Put your laser torch. Here, what you are going to see? You see, other than this normal reflection, there will be some intense normal reflection you will see here. You will see multiple points. You will see some another points here, some another points here, some another points here, something like that, faint points. So this what is happening there. This is actually a reflection grating kind of thing. It is actually giving. This is a normal thing. You will see that zeroth order reflection. Then you will see first order, second order. Similar way in the other side also, first order, second order you will see. Why? Because that size is actually comparable with that wavelength of your laser light. So your diffraction effect is happening. Why you are seeing rainbow in your CD? The same thing which we see in our, we solve in our one of our assignment. Nah? What will happen instead of a monochromatic light? What will, if your polychromatic light is undergone interference or diffraction? You will get a maxima of that one, but different wavelength will undergo maxima and minima at different angles. So you are going to get a colored thing. So the same thing is happening here. So grating is nothing. It will containing a, it will be something like a transparent thing. Then it's a transmission grating. It's a reflective thing. Then it's a reflection grating. So what it will have? It will have a, some grooves. This is something like a microscopic view of your grating. So it will have some grooves. So you can make something like that way. So what happens? And this size is actually will be some more comparable to that of your wavelength of the light. So at the edge, what will happen? Diffraction will can happen. So this can make like a different kind of thing. Either you can make like a, some half portion is completely opaque. This is completely opaque. This is completely opaque. So then what you are going to get, when light is transmitting, only some portion of this, only this portion will get transmitted. This portion there will not be transmission. This portion will get transmitted. This portion there will not be transmission. So actually what is happening, and there will be some interference from the lights transmitting from this portion as well as light transmitting from this portion and light transmitting from this portion. But because of this, half portions are completely opaque, which is light incidenting at this portion will not get transmitted. Light incident from this will not get transmitted. Light incident will not get transmitted. So what happens here? A portion of your intensity is actually lost, and the remaining portion is only get interference, and you are going to get some diffraction pattern. But some of your intensity is actually lost. That is in the case of a transmission grating with the amplitude. What is doing? Actually, you are modifying your amplitude, and some portion is completely opaque. So you are not going to get a proper fully intense. Your intensity is actually lost a lot. Now see, now this is a amplitude grating, because actually they are modifying your amplitude at a different position. Okay. Now there is a phase grating. There also you have some kind of grooves here. And I am saying that instead of making this area completely opaque, what I will do, just think that this is a particular material. Okay. I will put some another material above this one. And I am just going to remove all this portion above this one. I am just grinding this portion. So what I am going to get, I will get a different material at this region. This is also transmitting region, but this is a different material. So this is different material. So what happened? Light will transmit from here also. Light will transmit from here also. But what will be the difference? Because this is a different material, and light is traveling from this portion have a phase difference from light traveling from this position, because this will have a refractive index n1, then it will have a refractive index of something n2.
N2 and N1.
Yeah, so because of the same light, now I'm saying that I have a grating which have a same height. So I am making it in a manner such that the thickness is same, but here one material, here same material, here same material, here same material, here is other material. So what happened here? The light
What?
is actually, yeah, geometrically it is traveling the same distance, but optical path length from here to here will be, let it be like d. What is the path length light traveling here? n1.
D N1 T1.
Yeah, if it is a n2, then what is the light path length traveling from here? n2 d. Now see, so the optical path traveled by this position is this light is actually n1d, this is a n2d. So what will be the difference? n1d minus n2d will be your path length difference. And if the path length difference is something coming at lambda, what will happen? It will be constructive interference. If the path length difference is coming like lambda by 2, it will be, so this is same effect coming here now. This is your one light is coming here,
Yeah, that is right.
another light is coming here.
Phase difference.
Yeah, yeah. If it is exactly the path difference is coming at something lambda, what will happen? This will combine and form some bigger thing. Constructive interference will happen. And if the path length is when like this way, what will happen? Yeah, this crust and trough will combine and will form a, you will not get anything. You will get a destructive interference. Okay?
Right.
Yeah. Now this is the difference between your, so which will be more efficient, this phase grating or amplitude grating? What will happen in the case of amplitude grating? Half of your, no, we cannot say half, yeah, depends on the size of your grooves. Yeah, some portion of your light is actually not at all passing to the other edge, so some portion is actually lost. But in the phase grating, whether are you losing something? Actually light is transmitting from this also and this also, but because of the path length difference between the two light, actually interference happen. Okay. Yeah, now you are seeing now how we can calculate. Now let's go to our question. What they are saying, you have a phase grating, have a ridge height of 700 nanometer and a grating period of 2.2 micrometer was used with a, I see, ridge height of 700 nanometer. So now you have a grating having a ridge height of, so it's like a, yeah, I'm zooming it is more, so don't worry. They have a ridge height of 700 nanometers, so it has a height of 700 nanometer, and this groove period is like 2.2 micrometer. Actually this value is not needed. Okay, that is the characteristics of a grating, but for your calculation that value is not needed. So, and they are using a helium neon laser of 632.8 now. See, helium neon 632.8 wavelength with the normal incidence. the zeroth order has no light intensity with the laser source. So what they are saying, the zeroth order has no intensity with the laser source. So the direct light which is coming from here means, yeah. So the light which is coming from here has no intensity. So something happening. What is happening? Some destructive interference is happening with the zeroth order. Means the light which is coming from so what is happening? So let us see. This has a medium, and just think that there is no medium here. So the light is coming from here compared with the light coming from here. Not here means light coming from here is undergoing destructive interference. Okay, and it has a height of h. So what is the path length difference between these two? Let us have a refractive index of this medium is n1. Let it take it as 1. So what will be the path length difference? This will travel n1h.
Only n2h.
N1h, and the other one will only pass h. Okay, so here I am taking it as air. So this will pass a distance of h, and because of this medium having a refractive index n1, it will pass through a path length of n1h. So what will be the difference? N1h minus h.
N1 minus.
This is the path length. And what they are saying, for a helium neon laser of 632.8 nanometer, it is giving a no intensity. That means
Lambda by 2.
yeah, n1h minus h will be equal to lambda by 2. For what lambda?
0.
For lambda is 632.8 nanometer by 2. Because this is the first destructive interference criteria. Na? So this is the zeroth order interference, and that is coming as destructive. So that will be lambda by 2. Okay. Now we know that what we don't know actually here,
N1 we do.
n1 we don't know, h we know, or h we can take it outside, and n1 minus 1 will be equal to 632.8 by 2. How much? 316.4 nanometer. Okay, from here actually you can calculate n1 from here. So anyway, yeah, if sometimes if they ask you to calculate n1, you can calculate here, but yeah, that's not required. But yeah, anyway, if they ask for what is the refractive index of the medium, if they asked how you will calculate it, n1 minus 1 will be equal to 316.4 divided by h. What is h?
700
by 700 will be equal to 0.452. And what you will get? So n1 will equal to 1.452. This will be the refractive index of your medium. Okay. Now the question is not like that. Our question is, then the phase difference between the light passes through the the phase difference between the light passes through the ridge and valley of the grating is when if the laser source is changed to 488 nanometer. Okay. Now what you want? Now you want a 488 nanometer light if used. If you are using the same grating, if you are using a 488 nanometer wavelength, what will be the phase difference? Okay. If you know the path difference, you can find out the phase difference now. Now here you can see this N1 H minus H is actually your path difference. Okay. Any doubt?
That's right.
Correct only, na?
Correct.
And see that whether this path difference is actually wavelength dependent. Whether any wavelength is coming here?
No.
No, na?
No.
So we are thinking that wavelength is a constant and is independent of the, or the refractive index is a constant and is independent of your lambda. So as soon as we are considering this refractive index is a constant, it is actually independent. So N1 X minus H is actually the path length. Or if you want again from here, actually you can find out what is going to be N1 X minus H. But already we find out what is the value of N1 X minus H. What's the value? This one. 316.4 nanometer. Okay. You may have the doubt that this is coming because of 632.8 by 2. But yeah, this is why this 632.8 by 2 came, because we know that this is giving a destructive interference for 632.8. That's why it is came as 632.8 by 2. So we consider it as a 316.4, and this value is actually independent of any wavelength. This is a refractive index minus 1 into the height, and that value is a constant for that particular grating. Okay, this N1 X minus H will be a constant for this particular grating, and that is coming as a 316.4. So the path difference will be 316.4 nanometer, and this is a constant for that particular grating. Okay.
Right.
Now you see what you want to see. You want to see the phase difference for 288 nanometer. You have now path difference. This is a constant, and you want a phase difference. So how you will get a phase difference from path difference? Lambda is the path difference. Corresponding phase difference is what?
2 pi.
2 pi. So if theta is the, sorry, if L is the path difference, what will be the phase difference? L into 2 pi by lambda. From here it's okay, na? If lambda is corresponding to 2 pi, 1 will be corresponding to 2 pi by lambda, L will be corresponding to L into 2 pi by lambda.
Right.
Okay. So you know the path difference at say 316.4 nanometer. So you want phase difference. How will be? Your path difference into
2 pi.
2 pi by lambda.
Yeah.
What you will get? 316.4 into 2 pi by, what is the lambda? Lambda
That
is
is 488.
so 488. It's the 488 nanometer. So how much you will get? You will get some 4.7 0.07
Radians.
radians. So yeah, 4.07 radians, and you have a range from 3.9 to 4.2. So 4.07 is a 4.1. That's why they put 3.9 and 4.2 are the region. Okay. Now, in a reflection grating, if you want to cancel the zeroth order, what should be the height of the grating? Which I think actually, yeah, in the lecture itself, directly madam explained. You can explain that. Brief manner. Now, actually, what we cancelled? We cancelled in a refraction. Oh, sorry, we cannot say. Yeah, in a transmission grating, how in a phase grating, how this zeroth order is getting cancelled. This is the condition we put here.
E to the lambda bit.
Yeah. Now what is the case? Now actually we have a reflection grating. What is the reflection grating? So you will have a grating like this way, and this is a reflection grating. So there will not be any material dependence here. So this will be some mirror kind of thing. This will be also mirror kind of thing. This will be also. So light will not going to pass through this thing. What will happen? Light will incident here and come back, and the another portion of the light will incident from here and come back. So what is the path difference between these two light? Came from here and came from here. If this is H, light will come comparative to this light. The extra distance traveled by this light will be how much?
2H.
2H. And the path difference is 2H. And if 2H is corresponding to lambda by 2, what will have? Destructive interference. Then H should be equal to lambda by, this 2 will come here, it will become
4.
lambda by 4. Simple. Okay.
Right.
Reflection grating. This is the cancellation of the zeroth order condition, which will be H should be equal to lambda by 4. Okay.
Right.
Yeah. Now, yeah, another question here. Which of the following are advantages of a refractive optical element compared to a binary diffractive optical element? Okay. What is a refractive optical element? An optical element which is actually working in the principle of refraction. What are the things actually? Say lenses actually. Okay. Lenses or combination of the lenses. What is a binary diffractive optical element? This is the thing which we take a, it will be like a, depending on the grooves. What I mentioned sometimes before, it will be like a, it will be something like a lens. In the case of a binary refractive optical elements, it will be something like this. Okay. Now see what they are asking. Every system will have some flaws as well as some advantages. They are asking what will be the advantages of this refractive optical element compared with the binary diffractive optical element. Now go and see. Now actually you can go and see. It is easy to fabricate refractive optics as materials of a refractive index as are easily available. It is easy to fabricate refractive optics as materials of any refractive index are easily available. That is correct or not?
No, sir. This is not a correct answer.
Yeah. Why? Getting a proper refractive index of optics is also difficult, and fabrication is also going to be a difficult. Why? Because you can see
The
that
curvature we are doing.
yeah, it is like a complicated curvature you have to make rather than making like a groove. Okay. Next, refractive optics are less bulky. You can just see the diagram. Which is less bulky? Diffractive optics is less bulky or refractive optics is less bulky?
The second one.
Which is
Refractive.
which is a
The
less
second one, binary.
binary is a less bulky. Yeah. So actually you can compress that size of your diffractive optics in a single plane kind of thing. But your refractive optics will be always bulky in nature. So that answer is also wrong. So that is not the advantages of refractive optics. That's
Material
advantage.
saving will be there.
Yeah, yeah. Refractive optics have higher efficiency. That will be correct.
Yes.
Yeah. You see, actually the whole surface is acting as a refractive element, and the change in path length is also actually combining and producing a proper imaging condition. But what happens here, actually you are losing a lot of data, but yeah, giving some value, and depends on the how accurate or how efficient data you want. Actually you can make a diffractive optics as well as the refractive optics, but it is a binary diffractive optics. And so actually the normal case, actually there will be some curvature here and some curvature here and some curvature here, that are all actually moved to make the fabrication and cost effective. If you don't want that much accurate thing, then this is actually much profitable. Otherwise this is going to be more costly. Okay, so efficiency wise the refractive optics will be high, but yeah, fabrication and cost effectiveness in the case of the binary diffractive will be much more better option. That depends on your usage. It is easy to create if refractive and optics of any complex phase. So that is easy. No, making a refractive optics is actually very difficult task compared to your diffractive optics. Okay, so the answer is actually refractive optics have a higher efficiency. If you don't know the exact answer also, you can find out what are the wrong thing and take the which is other than wrong will be right answer. In the case of a single answer question, if it's a multiple answer question, you have to find out all the proper correct answer. Next thing, which of the following statements is or are correct? A phase grating is always a transmission element, which have an amplitude grating is always have a reflection element. Whether that's correct or wrong? I told phase grating is always a transmission element, whereas an amplitude grating is always a reflection element. What is an amplitude grating? And what is a phase grating? So I told what happening in the case of amplitude grating as well as a phase grating, na? But in the case of amplitude grating, what will have? There will be some opex region. And I said that light will not pass through that region, but that doesn't mean that light should always pass through that region. If it is opaque medium, in the case of an amplitude grating, either two things can happen. There will be amplitude transmission grating as well as an amplitude reflection grating. In the case of reflection grating, what happens? Light is incident from here, light will reflect. Light is incident from here, light will reflect, and these reflected lights are getting interference and undergo diffraction. Means a maxima or minima depends on your order of the diffraction. But in the case of a transmission grating, similar thing will happen. What is the difference? There will be one region, there will not be any reflection because this is opaque, and this is also there will not be any reflection. There will not be any reflection. This is not because of these are not opaque for transmission. What they will do, there will be something grooves in such a way that light, they will ensure that light will not reflect from this area. Light will not reflect from this area. Light will not reflect from this area. This is in the case of a reflection amplitude grating. But in the case of a transmission amplitude grating, what will happen? Light will pass through here. Light will pass through here, and the transmitted light will not pass through here. Transmitted light between from two grooves will undergo constructive or destructive interference and will give a maxima or min. But so you cannot say that amplitude is always reflection and phase is always transmission. Okay. So a phase grating is always transmission element, whereas amplitude grating is always a reflection element. Is actually a wrong statement. If phase grating has a better efficiency than an amplitude grating, that we discussed sometime before. That's true or not?
Yeah.
What will happen in the case of amplitude grating? Some intensities actually we are losing. Because of that, either that will be opaque or that will be about non-reflective. So you are losing some light intensity. So your efficiency is always getting decreased. But in the case of amplitude grating, phase grating, what happens? Light is transmitting from both the portion. But only the difference is that they are arranging, there's a phase difference, and based on the phase difference, actually you are getting a constructive or destructive interference. And actually, you know the difference between losing data and passing through constructive and destructive interference. You are losing data means that your data is not at all coming towards your output stage. But in the case of a constructive and diffractive interference, actually there is no loss of energy. Because wherever you are getting a constructive manner or destructive manner, it's like your waves are getting superimposed. It's not like your whole things are not at all come there. In the case of you are losing the data means this is not the effect of your interference. Your energy is not getting distributed. This already some energy is taken away by some means. So efficiency of phase grating will be always higher than that compared to your amplitude grating. Okay.
Therefore, the binary grating, it is always lesser efficiency, sir.
That binary grating is actually how you are comparing binary grating.
Whether it is amplitude or phase, we have to confirm.
No, binary grating. This is, you see this grating, na? This is actually a binary grating.
Yeah, there we will be
this why where you are using this one? This is you are using it only for grating purpose. You are saying binary grating is less efficient comparing with actually one lens. Actually, you are making it as a Fresnel lens. Okay. And corresponding to this Fresnel lens, actually you can make a binary grating.
Equivalent.
Kind of thing. So if you are comparing efficiency of this one to this one, the efficiency of because this is actually containing your amplitude information also here, but this actually you will have a equal amplitude at all the phase. Actually comparing with the one, the two will have a less efficiency. So it is not like this grating and this grating you cannot compare. This is actually in the case of a Fresnel lens, you are taking a binary grating as your Fresnel lens, then that binary grating will have a less efficiency compared with the Fresnel lens which have the amplitude portion also. That's the thing. In the case of a normal grating, almost all the grating will be in the form of a binary also, and you will have some sawtooth kind of grating like this way. So if you are comparing that efficiency with this thing, but these are actually complicated things. You don't have to go like this way. So you are seeing this one now, this grating, this kind of binary grating and a sawtooth kind of thing, binary grating. So in this case, the sawtooth will have more efficiency compared with this binary grating. Okay, these are the kind of comparison. So you cannot just compare like a normal grating with a Fresnel lens or something, because the normal grating actually you can compare with a normal binary grating with a sawtooth kind of grating. So in the case of sawtooth kind of grating will have more efficiency. Or you can compare a Fresnel lens which have a binary grating system compared with a Fresnel lens with a amplitude system also. In that case, Fresnel lens with this amplitude system will have more efficiency compared with the Fresnel lens made with the binary grating. Okay,
Right.
and yeah, in the case of a binary grating, the binary grating itself will, you can make it as a amplitude grating as well as a phase grating. So a binary grating have a amplitude grating manner has a less efficiency compared with a binary grating with a phase grating. Okay. A binary diffraction grating of a fill factor of a 50% and a grating period of a 2.1 micrometer is illuminated using a laser source having a wavelength 532 nanometer. Theoretically, the percentage of energy in the fourth diffraction order. This actually you have to check how your fill factor is actually depending on your amplitude distribution. So where you are supposed to check actually you have to remember that that particular diagram. Madam, show one diagram now. So it's like not a numerical calculation you cannot do. You are hearing now? My voice is
Yes,
visible
sir.
now. Yeah. I thought that I lost my connection. I think I'm losing my connection. You are hearing?
Yes, yes, sir.
Okay. But I'm not getting internet connection here. Yeah, there is no problem with internet. So,
Some curves were given, sir.
but
Some curves, so it would be the percentage of energy.
yeah. That curve actually you have to go through.
Yeah. And in the that one 50-50, there was a
Yeah.
gap.
Yeah. You can
For the
see that.
first order, it was a gap, it was there.
Yes. So you can see that in that one. Yeah. But yeah, I don't know. I'm getting Google Meet, but yeah, I'm not getting any other internet.
I
Anyway,
happen to see in that.
you can see my screen also now.
Yes, I am able to see.
Okay, that is good actually. But yeah, I'm not getting any internet site here. But that's okay. So in that case, yeah, go through that curve and you can see that in the case of a second order as well as the fourth order, you are coming, that curve will come like it is actually the mid portion of the curve, and you will see that it will be like a zero portion because you will not have any efficiency there.
Right.
Now the last question. The period of a binary diffraction grating controls. What are the things? Distribution of intensities in the different orders. That's actually coming from the earlier question. The distribution of intensity is actually controlled by what? The distribution of intensity is actually controlled by your duty cycle.
Yeah, you can say it. Yes.
Yeah, the distribution of frequencies depends on actually like a duty cycle rather than your thing. So it will have a particular distance or period, but it can have a different duty cycle. Let us say like a 50% duty cycle. This is like a 10% duty cycle. So depends on the duty cycle. Actually, your distribution of your energy is actually vary. Okay.
Right. Yes.
Yeah. So that is not the answer. Do people see my screen? So maximum efficiency of the grating. So distribution of intensity is actually, yeah. So the efficiency also actually depends on the how the intensity is distributed. So you cannot say maximum efficiency is also not actually depending on your period. Next is actually your diffraction angle. So diffraction angle is actually depends on your period. So if you are changing your period, actually your diffraction angle will vary. Why? Actually because of their, when your periods are coming less, what is happening, the diffraction effect is coming more, and your bending of the light will also increase more. So actually diffraction angle is actually depends on your period of your diffraction rate. Now you see, then the next question is like a space in between the diffraction spot. What happens in the case of a space? So just see that you have a lot of grooves here, and you are have a zeroth order diffraction, first order, first order, second order, second order, and you have a screen here. So this angle is actually depends on this theta 1, this theta 2, or this theta 2, this theta 1. This angle is actually depends on your period of these grooves, and you can see the spacing between these spots is actually depends on this angle. If your angle is more, the spacing between these 2 points will be more. If angle is lesser, the spacing between the 2 points will be less. So if your angle is, spacing and angle is actually, you can say it's a directly related. So, and the angle is actually related to your grooves size or the groove period size. So if you are having a groove periods variation, that will affect your angle variation as well as the spacing between the diffraction spots. So your answer will be
C, right?
diffraction angle as well as the spacing between the diffraction spots. These are the things. Okay.
Right.
So any doubt regarding all other things? Or you people want some more session, for just if you want to make our thing such that if I will check whether I'm having some model question or something, I can just share that question such that you people can answer. Or if you have some model question, if you want some session like this kind of thing, such that you can do some practical kind of session, you can do. What will be what will be your interest? Let us go like that. And trying to get some model question like yeah, some previous year's assignment or something
Okay.
like that will available. I will check.
So are you going to give questions right now?
Not now. I will check. I want to check some model question may be available. Model means it's not the original model. Yeah, it will be like some previous year's assignment question, like that. And we can see what is
Tomorrow you will give, sir? Today, sir?
tomorrow. I will check either. Yeah, actually Wednesday I have some practical duty. So when is your exam? Friday or Saturday?
Saturday only, sir.
Saturday. Okay. If the question is available, I will post in that in our group such that you people can try. Or yeah, if you have some doubt, you can ask here. Or no problem.
Said like you'll give essay type questions today.
Essay type questions. Okay. That yeah. Anyway, yeah. You people can go through the sessions. So I cannot say exactly what will be essay type questions, but yeah, let us see. You people also see. You can check and tell. Let us see. Anyway, let us go through this one. And you people can understand now what kind of essay type question can come here. But I don't think it is going to be a big essay type, because since these people are telling that you may have to enter it on your system only now. So I don't think it is like a big essay type. So geometric optics basics, what you learned in this thing. Refraction through a single surface. Actually, yeah. In this one, you can see now. So you may have go through this kind of things. How that derivation of your refraction is coming, and that derivation of that refraction equation. Nah? That's a big derivation of our refraction equation. So just go through that one also. I'm not sure whether that kind of big question whether they will ask for examination, but yeah, I'm feeling. You see, in the week one, what will be the or the week two? Week one is I think it's like a comparatively simple. Week two,
Snell's law.
yeah, yeah. Snell's law, derivation of the Snell's law, yeah. And there are like a yeah, derivation of the Snell's law is a thing such that yeah, that you have to remember. And the refraction through a curved surface also. Using Snell's law, you can derive the refraction of through a curved surface and arriving one equation. Na? 1 by v minus 1 by u, or 1 by u plus 1 by v is equal to n minus 1 into 1 by r1 minus 1 by r2 kind of thing. And 1 minus 1 1 by r.
Equation.
What?
Thin lens equation.
No, before the thin lens equation is comparatively simple. Before the thin lens, you are directly arriving from your first principle to your curved surface equation from the Snell's law. So actually, thin lens is a combination of your two curved surface such that from there thin lens equation will be comparatively simple. But you derived a curved surface equation using your incident angle, refractive angle, and the normal at the incidence like that way, and you put some cosine equation and other things kind of thing. You remember? So that is a little bit bigger. The problem is that it will not be a. If you have enough time in it, you can solve. But the problem is that time will be something limited, and if you don't have the practice of solving these questions, the problem will be like within that particular time. Sometimes you can become blank also. That's a thing. That this kind of problem I used to face. That's the thing. if I didn't solve in a or kind of this kind of questions in a much manner such that I can go through the all steps in a fast manner. Sometimes if I want to think at that moment, sometimes automatically I feel just getting blank. So yeah, if there are some lengthy question, you while reading you feel that okay, this will like easy only, but yeah, question will be easy only. But the thing is that since you didn't practice by writing and doing some 3 4 times, when suddenly you see in the question and in between some confusion came, that can be more troublesome.
No, it will be difficult on the sir. Putting a mathematical equations and
uh,
everything, it is there.
yeah, that I'm thinking. So I don't think it is like that kind of big question may not come, but
Yeah,
yeah, but
mathematical putting on this and mathematical formulas and everything, it takes a
uh,
lot of time.
yeah. So so yeah, typing in the typing also, I don't know whether they will ask that kind of question, but it's better you familiarize with the equations. So that will not be like a problematic, and you can be confident also. So I think that there are not a much bigger questions are available here. So you don't worry like that way. Yeah, Snell's law. Using Fermat's principle, you can derive Snell's law also. That also you study, na. That is actually yeah. It's containing actually less equations also. Using Fermat's principle, you are deriving like a yeah, whereas Snell's law of refraction as well as reflection. Like I equal to R also you can derive using Fermat's principle. Using sin I by sin R is a refractive index also you can derive using Fermat's principle. These two things are actually like yeah, I'm feeling like it can be like some essay type of questions. But yeah, these things actually you just try to derive. These are actually that some bigger questions other than like a numerical solving of the answer. Then here this aperture stop and other things, yeah, this can come like a, I don't know whether it may not come like a essay type questions, but yeah, it will be like exactly problem solving kind of things. Or yeah, based on that one. Anyway, I don't think yeah this they're not going to give Oslo as a question, but yeah, Oslo based image can be come as a question. They said so. You should be familiarized with what are the sometimes if they see give some ray intercept curve and ask for yeah what kind of aberration this one you may have to answer, and you see something like yeah there are different aberrations and how they are looking like, or if how they can be get corrected, these things are there na, that things actually you go through. Anyway, this will not be a big issue, but thing is that you people may have made notes while reading that or going through this video, whether you people made notes of your own.
Sort of, sir, but they are not that proper for
Whether
me.
the direct notes are available here, lecture notes available, na?
Books and lecture notes are there, sir. Yes.
Yeah, I think yeah, you can go through this one because yeah, while revising, I don't think it's like going through the entire video again will consume a lot of time. So yeah, if the lecture notes is actually the exact notes of that thing, na? So I think that will be much better option.
Yes, sir. Lecture notes has all the PPTs.
Yeah, then that will be good, such that you can go through in a fast manner, such that you can understand. Because anyway, you people already go through this one, so it will be like you can understand what are the things. And lecture notes is exactly like what madam telling. They are actually converted into notes, na. So that will be
Yes.
good.
Sir, that I think it is in the books section.
Okay, okay, yeah.
Yes.
So ray tracing matrix. Okay, ray tracing matrix also. Yeah, yeah. This can be something like essay type question in the case of like a deriving of imaging equation for a thick lens using ABCD matrix. So you have to know the ABCD matrix of translation, reflection, refraction, and refraction through curved surface, thin lens. These all things you have to know: translation, refraction, refraction through curved surface, Reflection may not be that much important, but yeah, these things actually you want to know such that you can get a ray tracing equation for a normal matrix. And the matrix multiplication, you don't forget it. Yeah, that will be some more important. So yeah, the way question can be very simple, but yeah, if you mess it up, that will be losing some marks. But I don't think this exam will not be very tough. Don't worry about exam. Yeah, revise. Yeah, different kind of operation. I think that will be a good question. Will must be the in that case. So that's the main part. And yeah, monochromatic aberration. Yeah, that also. In this case also, actually, yeah, there are different images you can see and say this is this kind of aberration. So in the case of monochromatic aberration as well as your chromatic aberration, you can see there are some images madam already saw. So you can expect some similar kind of images, and there will be a question like what kind of aberration is this, and how you can correct this aberration, that kind of a question. If you say that if you see some chromatic aberration and how you can correct this question, if they ask, you are supposed to answer. You see some colored thing, then you can directly say it's a chromatic aberration, and how you will correct that chromatic aberration. It's a some simple question I am saying, but just say you are seeing some image which is containing a color spread at the edges. So what kind of aberration is that one? That will be some chromatic aberration. And how you are going to correct it? What is the simple method of correcting a chromatic aberration? What you will use for correcting a chromatic aberration? Just one sample. What will do? Nobody have answer?
Having two lenses together.
Yeah. What you call it that one?
Uh,
Yes, sir.
I forgot. But I think two lenses, if we have together with different Abbe numbers or something, we'll
Yeah.
be able
One
to
by one.
eliminate.
That has a name. That two lens together will have a name, na?
Unicorn.
Doublet,
Yeah.
Unicorn.
What doublet?
achromatic doublet.
Yeah. That is called achromatic
Okay,
doublet.
yes,
Okay.
yes,
So yeah, this kind of terms you should not because if you want to type, if you have an option, then it's okay, we will understand it easily.
yes, sir,
But
yes.
yeah,
Okay.
yeah, this kind of, yeah, if they ask you give some gap and ask you to type there, then it is going to be a problem if you didn't remember that exact name of that. Okay, so that you also don't forget. Maybe Oslo. Yeah, this Oslo images also you see, and you can see that okay, something, some ray interceptor curve, and you can see that okay, this is a corrected thing, and this is a uncorrected thing, kind of things are there. So just go through. But yeah, first you go anyway, go through all the theory part, okay, and this also, this kind of the ray interceptor curve and that theory also you go, and yeah, if you see some images made by Oslo, you are supposed to understand that. So this thing, how you will correct the chromatic aberration and aberration corrections and this kind of thing, astigmatism. There are different kind of things now, and there are like there are some ray fan diagram, some kind of aberration coming from coma, and some kind of aberration is coming from distortion, some kind of aberration coming from your curvature. So these kinds of different images are there. So don't forget to see and understand this kind of things. This may be looking like symbol, but yeah, it's like if you are already see this one or just go through that one, this may be symbol. But yeah, if you didn't or if you couldn't do pay attention on that one and that came as a question and you have some confusion like that, whether it's like a curvature effect or it's like a distortion or something like that way, then you will feel bad that only. So this kind of a symbol thing, don't forget to miss.